All right, today we're jumping right into a cosmic detective story, one that takes us to the very heart of our own sun. For decades, there's been this fiery riddle that has completely stumped scientists. But a brand new paper, well, it might have just uncovered the smoking gun. So here's our game plan for cracking this solar case. We're going to start with the riddle itself, then look at the existing clues, introduce a fascinating new theory, and see how a virtual sun, of all things, helps solve the whole mystery. And finally, we'll get into why this all matters. Okay, so every good mystery needs a really compelling setup, right? And believe me, our sun has a major one. It's kind of like it's running a million-degree fever, but not in the way you'd probably think. And this right here is the central paradox. Think about this for a second. The sun's surface, the part we can see, is about 5,000 degrees Celsius. Hot, right? But its outer atmosphere, the corona, absolutely sizzles at over 1,000,000 degrees. How is that even possible? I mean, it's like standing 20 feet away from a campfire and feeling way hotter than you would if you actually touched the burning logs. It defies simple logic. And it's one of the biggest unsolved problems in astrophysics. Now, our main clue in this whole thing might just be these solar spicules. For about a century, we've seen these incredible jets of superheated gas, plasma, just constantly shooting out from the sun's lower atmosphere. They look like a field of fiery dancing grass, and they just might be the key to figuring out how all that energy gets transported upward. So if spicules are our clue, we've got to figure out what creates them. And this brings us to the usual suspects, the existing theories, and a pretty critical flaw in their story. Look, scientists have had some pretty solid ideas. One of the most popular involves something called P-mode leakage. Basically, think of them as sound waves from deep inside the sun that kind of leak upwards and push material out. And that works pretty well for the shorter specules. But here's the problem. It hits a wall, a literal height limit. It just can't explain those monster specules that tower over 6,000 kilometers high. And this isn't some tiny little detail we're talking about. The source paper we're looking at makes it crystal clear. The way these giants are formed is fundamentally unknown. That means a really crucial part of how the sun works is basically a complete black box. But then, a fresh lead in the case. A 2025 paper from a team led by Isha Sharma has introduced a totally new idea. So let's see how their theory paints a whole new picture of what could be happening up there. And their big idea is surprisingly simple, really elegant. They asked, what if it's not just one force at play? What if it's the combined effect of two different kinds of high-frequency wobbles on the sun's surface, both acting together? This powerful 1-2 punch is the new clue right at the center of their whole investigation. So what exactly are these wobbles? Well, the first one is a pressure perturbation. Just imagine it as this up and down pulse on the sun's surface, kind of like a drum beat, sending out these sound-like waves. The second is a torsional perturbation. This is more of a side-to-side twisting motion, like you're wringing out a wet towel, and it generates these incredibly powerful magnetic waves called alpha waves. Okay, a great theory is one thing, but you gotta test it, right? So the researchers decided to recreate the crime scene. Not on the sun, of course, but inside a beast of a supercomputer. They did this using something called an MHD simulation. Now, don't let the name freak you out. You can basically think of it as a super realistic weather forecast, but instead of rain and wind, it's for solar plasma. It uses the laws of magnetohydrodynamics to perfectly model that complex dance between magnetic fields and superheated gas on the sun. So their virtual sun had all the key layers. The simulation kicked off the wobbles way down here on the surface, then it tracked the waves as they shot up through the lower atmosphere, where the spicules are born, and they just watched to see if those waves could violently shove this boundary, the transition region, way up towards the corona. So, the team set up their virtual sun. They programmed in those two wobbles, and they hit run. And what came out of that supercomputer was absolutely stunning. This, my friends, is where we find our smoking gun. It worked. It just worked. The simulation showed that combining that up and down pulse with that side-to-side twist, that was the secret sauce. Together, they had more than enough power to launch these towering jets of plasma that looked exactly like the tall spicules that nobody could explain before. And this right here, this is the key piece of evidence. This graph from the paper shows the height of the spicules from the simulation plotted against the timing or period of those wobbles. And just look at that peak. It shows there's a sweet spot, The absolute tallest spicules were made when the waves had a period of about 110 seconds. And just how tall are we talking? Well, the spicules in the simulation reached heights of over 20,000 kilometers. Remember that 6,000-kilometer barrier that stumped all the other models? Yeah, this new theory just blows right past it. Case of the missing heights solved. And hey, don't just take my word for it. The researchers say it themselves right in the paper. The taller spicules form precisely when you get the wave period and the atmospheric conditions just right, exactly what their model predicted. But hold on, the model revealed something else. Remember the other part of the mystery? That superheated atmosphere? Well, scientists have calculated exactly how much energy is needed to keep the sun's lower atmosphere that hot. And the number they came up with is about 10 million ergs per square centimeter per second. Now I know, that's a mouthful. Just think of it as the energy budget the sun has to meet to explain its fever. So here's the kicker. When the researchers actually measured the energy carried by their simulated waves, it was more than enough to meet that energy budget. So their model didn't just solve one mystery, it was a two-for-one deal. It explains both the crazy height of the spicules and provides the missing energy needed to heat the sun's atmosphere. So case cracked. Awesome. But why does solving this one puzzle matter so much when we're trying to understand the bigger picture of our star? Well, let's just quickly recap what we've learned. First, we now think that combining two types of waves is what creates those mysterious tall spicules. Second, those same waves carry enough energy to explain the sun's atmospheric fever. Third, this whole thing creates an incredible link between tiny little wobbles on the surface and massive eruptions high above. And finally, it gives us a crucial piece of the puzzle in understanding how the solar wind, the stuff that affects our entire solar system, even gets started. What this research really gives us is a powerful, unified model. It's a single story that makes sense, connecting the dots all the way from the sun's churning surface, up through its insanely hot atmosphere, and all the way out into the solar wind that flows past Earth. And that leaves us with one final thought. If something as small as these little surface wobbles can drive such enormous events, well, what other huge secrets about our star are just hiding there in plain sight, waiting for us to find the right connection? Thanks for watching.